All right. Good morning. Good afternoon, everyone. Welcome to the HoTTEST Summer School. This is the 8th lecture in the summer school. It is the 5th lecture in the homotopy type theory track, as opposed to the AGDA track. And it's the second by Ulrik Buchholtz. Last time he told us about universes, and today we're going to, and propositions as types. And today we're going to hear about equivalences. So Ulrik, please take it away.
Thank you very much. Yeah. So last time we did universes and we rounded off the basic structure of type theory. Let me just make a little picture of a universe in case someone was still struggling with what it all means. So we'll start drawing types sometimes as bags of points or lines, just like we draw sets in school. So a universe is a bag of elements, and so it's the idea is that it has things that represent a lot of types. It's not all the types, but at least maybe all the types we could build without universes, and maybe some smaller universes and things we could build with them as well. So there's going to be an element in the universe corresponding to the empty type, and there's going to be an element corresponding to the unit type, another element corresponding to the natural numbers, and then maybe the way we can represent this, maybe we call that the universe is not just a type, but it's also a type family, because we want to be able to decode an element of the universe to the type that it represents. So we can draw this as a kind of bubble diagram. So here over the term in the universe representing the empty type, there's a type, and that type is the empty type. And over the point representing the unit type, there is a type, which is the unit type, which has one element in it, which is the star. And over the natural numbers, there's going to be a larger type, which is going to be the actual natural numbers, and so on. And then if you have some terms for types in the universe, you could build terms for sigma types, sigma x and y, and maybe a pi x and y, and so on. And over those will be the corresponding decoding. So formally, we had to separate terms and types. So the empty type is a type, so the term for that would be some code for that, and likewise for the natural numbers. And then when we formally want to decode, we use this t operation. If x is a variable of type u, then t of x is an actual type, and this is going to then, so here t of the code for the empty type is the empty type, and so on. So here is actually the unit type, and here's the natural numbers, and so on. Okay, so that's just a picture of a universe. And as I said, maybe if U is a large universe, you may have a code here for a smaller universe, and things you might build out of those. There are also co-products and stuff like that. Obviously, you can't draw everything in the universe. Okay, so now we go on to today's topic, and this is equivalences. And to define equivalences, we need the notion of homotopy, which then finally brings together everything in the name of the subject, homotopy type theory. And we give one particular definition of equivalence. We'll have another one next lecture. A lot of what we do in homotopy type theory is think about what are the identity types of elements of types. And today we're going to give a very concrete description of what are the identity types and sigma types. And what function extensionality and univalence do is actually describe the identity types and other types. For function extensionality, it's going to be for pi types, and for the univalence tells us about the identity types in a universe. Okay, so let's go on. So one thing I was going to say last time, which I think is appropriate to start with this time then, to motivate the notion of homotopy, is to look at the propositions as types interpretation. Of a function being surjective. So it's if let f be a function from a to b, and we want to say what type should express f is surjective. Okay, so that's what I'll say something about. So recall how we do it. We say, well, usually f is surjective. This means that for every y in b, there exists an x in a such that f of x is equal to y. So we make the quantifiers into pi's and sigmas. So we get a pi over y in b, and then a sigma over X in A. And then equality becomes the identity type. So this is F applied to X is equal to Y. Okay. So if we want to draw a picture of this, so we think of A as a bag of stuff and B is another bag of stuff. F is this map. And it says that for any Y here, there's some X. And then when I apply F, I get some element of B, F of X. And then there has to be this element of the identity type. So draws an equation with maybe that has a direction that goes from F of X to Y. So that's how I might represent it. But then recall that we ended up last time by discussing the principle of type theoretic choice, which allows us to, if we have such a pi sigma combination, you can go back and forth between having a function from Y to X or from B to A, and then separately you have the condition that is that this holds. So it's a kind of choice principle that you always have whenever you just use the propositions as types of Curry-Howard interpretation of quantifiers. So by type theoretic choice, this amounts to sigma of a function g from from B to A, and then for every y and b, we have f of, so the x is now g of y, so f of g of y is equal to y. Okay, so if we think about what this says, it says that we have now a function that goes in the other direction, the g. So the g picks out such an x, and then we have this other component here, which says for every y and b, the composition f after g applied to y is equal to y. So this is a relation, a kind of relation between the composition f after g and the identity function on b. But it's a priori weaker than having an identification. So f with g equals the identity in b in this function type b arrow b. Okay, so this relation is what we're going to call homotopy. Okay, and maybe I'll just as a preview for what we're going to say later. If this relation holds here in this particular case, we say that G is a section of F, or what it's the same thing, that F is a retraction of G. And you might think of this as a kind of stronger version of being surjective, and you could call it that F is split surjective. But since this expresses that there is some G that is a section of F, we might also say that this is the type of sections of F. We'll redefine these types later on. Oh, and I want to make one more comment before I go on, which is that the notes that I'm looking for that I have prepared for this are up on the GitHub page. So if you want to follow along, if I flip through things too quickly, you can get most of, you can flip back live by looking at that PDF on the GitHub page. Okay. So now let's formally define homotopy. So Actually, I'll give one more example to motivate things first. So here's another example. So we can define the negation on the Booleans. I'm just going to call it neg here. Just save a little bit of writing. I think in the book it's called neg-bool. And by pattern matching or if then else on the Booleans, we could say that negation of true is false. Oops, it's not a very nice. And the negation of false is true. Okay, so then if we make this definition, then if we do this twice, so the negation of true, this will be definitionally equal to negation of false, which is true. And the negation of false is definitionally equal to false, so judgmentally equal to false. However, it's not the case that if you have a variable of type bool, then it's not the case that the negation of B is not definitionally equal to B of type bool, at least the way we have set it up. One could imagine another type theory where this was the case, but it would be very slow to perform type checking if you added this as a definitional judgmental equality. So we don't have that because the negation function there's no reduction equation if you just have a variable. So it's also not the case. So also, take the composition negation with itself. This is not definitionally equal to the identity function on the Booleans. However, by induction on the Booleans, we do have an element of the pi type. But we have some element, I'm not going to write the name of it in the pi type for every b in bool. Oops, it should be lowercase. We do have an element of neg compose neg b in the identity type, so equal to b. So we have this by bool induction. Okay. Another way of saying this is that so this composition of negation with itself and the identity function of the Booleans, they're pointwise equal, as expressed with the identity type. Okay, so this is, if you like, an instance in ordinary mathematics or set level mathematics of the notion of a homotopy, because that's exactly what a homotopy is, as we'll now define. Okay, so here comes the definition. So let f and g be elements of a pi type. We're defining this for dependent function, not just for functions, because that's useful and because, well, we like to study what the identity types in all types express, including the pi types. And so we might as well do the dependent case if you want to also study the non-dependent case. So let f and g be dependent functions. So this means A is a type and B is a type family over A. And then we define a new type, F homotopic to G. And it's this pi type of pointwise equality for every x in A. F of x is equal in the type B of x to G of x. So this is the type of homotopies from F to G. Okay, so we just saw an example of a homotopy. we have homotopy H from the negation composed with itself to the identity function on the Booleans. Okay. So we'd like to draw some pictures of homotopies, and I'm going to introduce a way of drawing dependent functions and type families. So let's first look at a special case where we have a non-dependent function type. So the special case where B doesn't depend on X. We might draw it as follows. So let's say I'm going to draw A as a sort of one-dimensional thing, but it could be a bag of things. Let's say we have an arbitrary element X and A, and we have these two functions, A to B, non-dependent functions. And let's say we're drawing B as this bag of stuff. So if I think of A as this little line segment, this means that the image probably will look like some sort of line in B. Maybe this is the course of values of F, and this is the course of values of G. And let's say F of X ends up here, and G of X ends up here. So this homotopy is that gives for every X a path or an identification in B from F of X to G of X. You have this everywhere. Now, how should you draw a picture of a dependent function? Well, just like you draw pictures of graphs in analysis or ordinary calculus or something like that. So that in general, we can draw a type family. Again, we draw the base, usually some sort of line segment, and then dependent function is then some family of types that changes as we run along A. So here, for every X, I get this type of elements that lie over X. So B of X contains all the Y's that lie on this line here. If you think about how you draw graphs of functions in analysis, well, then you have some sort of rectangle, because you have an X-axis and you have a Y-axis. And what changes in dependent functions is that the Y-axis depends on where you are on the X-axis. You get a different Y-axis, and that's all that happens. So the graph of the function F might be something that looks like this, while the graph of the function G might look like this. Now here in this picture, I don't have like dimensional room to make little squiggles on the G, but that's just a defect of drawing a two-dimensional representation of this. A lot of people find these pictures helpful. That's why I'm telling you about them. And if you don't find them helpful and you just prefer the formalism, that's totally okay. It's just another tool to have to think about type families, and dependent functions. Anyway, in any case, the homotopy from F to G should give for every X now an identification in B of X, which is here this little one-dimensional thing. So here's our H of X. And then the homotopy should do that for all X. Okay, so the way to think about maybe this blob here is that it puts together in a sigma type all the B's. We'll later think about elements in the sigma types as a pair of an X on the X-axis and then a corresponding Y somewhere on the corresponding Y-axis, which is the B of X. And then think of, if you want to go from anywhere in the blob and you go vertically down, that's taking the first projection. Okay. So that's how we will represent this. Okay. Now, what can we do with homotopies besides give a proof of something like this, that the negation composed with itself is the identity? Well, we can, let's see here. we can define what it means for the diagram of types and functions to commute. So let me just define that quickly. Commutative diagrams. Okay. So to express that a diagram of types and functions commutes, we can use homotopies. And since no one knows how to express a general definition of diagrams in type theory, we'll just do this in particular cases when it comes up. So if you don't understand what a diagram is, don't feel bad about that. We'll explain when we have particular instances how to formalize it. So a simple case is a triangle. So you have three types. Let's say we have A, B, and X, and three functions. F from A to X, G from B to X, and H from A to B. Then we would like to say that this diagram commutes, which is just a way of saying that no matter where you start and you follow some arrows, you end up in the same place. But of course, that might be some extra structure, and that's extra structure is given by a homotopy. So we express this by saying that we should also give an H of the type of homotopies from, in this case, let's say from F to G after H. And then we might draw that in here, say we have really had to a piece of data, we have this tilde in this direction, let's call it capital H. Another small example of a diagram would be four different types, let's say A prime, and B prime. We have functions F and F prime, and G and H. And to say that such a square commutes, oops, I'm going to call this H. To say that the square commutes, we add a homotopy. So the only place we can start and go different places is we start at A and we can go either this way or that way. So we add a homotopy H of type H after F, should be homotopic to F prime after G. And we draw a tilde in here, maybe give it a direction, let's say that's a homotopy in that direction. Okay, so that's how we can formalize the notion of at least in particular cases, of a commutative diagram in type theory. All right. Now, so far we haven't seen any examples of homotopies of dependent types, but this can come up rather easily if we have the notion of a homotopy of homotopies. So that's the next thing I want to explain. Homotopies of homotopies. So let's say we have, again, two elements of a pi type. And we have two homotopies. Say we have H and K, both in the type of homotopies from F to G. And let me just, I'll spell it out. This type is judgmentally, by definition, the same as the pi type for every x in A. F of x equals G of x. But okay, but exactly because it's a pi type, it makes sense to form the type of homotopies from H to K. So we have a new type of homotopies from H to K, which by definition is the pi type for every x in A. H of x equals K of x. So if these equations are in B of x, then these are identifications in the identity type F of x equals G of x in B of x. Oof. That's an iterated identity type. So if you want to draw a picture of it, let's say for every X and A, and now to have some room, I definitely need a two-dimensional surface. So I'm going to draw B of X as a whole blob. And let's say I have my point F of X here and a point G of X here. And one way of identifying F of X with G of X going this way. And this is my H of X. And I have another way going this way. And that's the K of X. Then an element here, let's say we have an alpha of this type, and alpha of X should be a way of an identification of the paths. Directed that way. Okay, and then if you had two alpha, if you have an alpha and a beta, then you could form the homotopies of the homotopies, etc., etc. Okay, but we won't need that just now. Just nice to know that we have at least the machinery to talk about it. So now let's talk about some laws. Laws for homotopies. So recall that we have what is called in groupoid, or at least the beginnings part of the infinity groupoid structure on identifications equations, and we can lift this structure just pointwise to homotopies because homotopies are pointwise equalities. So we write it down. Since homotopies are pointwise identity types, we can lift laws and operations. Well, usually we implement laws as operations, but maybe we think about them in different ways. On identity types. Oops. Pointwise to homotopies, to the type of homotopies. So for instance, we can give a witness that the homotopy relation is reflexive. Reflexivity of homotopy. So let's see, fix a pi type P. Let's see, P is some pi type for a type family B over A. And then reflexivity says for every F and P, F is homotopic to itself. And this term says lambda F refl at F of X. Lambda F lambda X refl at F of X. And likewise, you can give an operation, then it inverts a homotopy. So say for every F and G and P, if you have a homotopy from F to G, then you get a homotopy from G to F by pointwise taking the inverse of the identification from F of X to G of X to get an identification G of X to F of X. And we're going to write this as H goes to H inverse. We can also concatenate homotopies. So if we have three elements of the pi type, F, G, and H, then F is homotopic to G, and G is homotopic, oops, G is homotopic to H. Then you get a homotopy from F to H by pointwise concatenating identifications, and we're going to write that as sort of a fat dot. So that's in the diagrammatic order. So, and then there with laws. So for instance, we can give a witness that this is associative. So this would say that if you have 3 homotopies that I can concatenate, and let's say H, K, and L, and if I first concatenate H and K, and then concatenate onto L, well, that's going to be homotopic to first concatenating K and L, and then concatenating H. Because point-wise, I can use the proof that concatenation of identifications is associative. And likewise with their unit laws, there are laws for inverses, inverse laws, etc. For higher dimensional laws of the laws and so on. Okay. There's one new thing that's not just pointwise that we can do with homotopies that you can't just, that is new because we're working with functions, and that's whiskering. Whiskering. So what is whiskering? There are 2 different instances. So if so you have 2 functions that are parallel, f and g go from a to b, and then you have a function that you can compose with from, say, from b to c. So we might draw that as I have a, b, and c, and then I have f and g, and then I have this function h, and I have a homotopy from f to g. We can draw that in the picture as tilde in this direction. It's hard to see. That's an H. That's an H. Then we can make a new homotopy, H whiskered with capital H. And that's going to be a homotopy from the composition this way to the composition this way. So that is from H after F to H after G. And what's the definition of this homotopy? Well, for every x, so it's for lambda x in A, I can take the action on paths of H on a capital H of x. So this is an identification f of x equals g of x, and then I take the action of paths of H, and then I get h of f of x equals h of g of x, which is exactly what we need for such a homotopy of the composed functions. But of course, you could also do it on the other side. So if k is a function from B to A, then, and now the picture is I have A, B. I again have the same homotopy H here, which goes in this direction, F to G. Here's the function K. We get a homotopy capital H whisker K, which is a homotopy from F after K to G after K. And the way you put it together is you say lambda, say y and d. And well, I need to give an identification of f of k of y to g of k of y, but I can just use the homotopy H at the point k of y. Okay. And I'll leave you to think about how much you can generalize these operations to dependent functions. Maybe you can't make everything dependent, but you can certainly make some of it dependent. But we don't need that today. So now comes the definition of a bi-invertible map, which is our definition of equivalence. But I'll title the slide bi-invertible maps. Okay, so for the definition, we fix a function a to b, and then we make 3 different definitions. So the last one is going to be what it means for F to be an equivalence. And an equivalence is going to be, as I mentioned in the introduction, a kind of way of saying that it should be what amounts to, at least if A and B are both U small types or live in the same universe U, a way of identifying A and B in that universe. But we put it together out of two simpler ingredients. And in fact, we've seen one, almost seen the other before. So one of them is the type of sections of F. So this is a dependent pair of a G going in the other direction and a homotopy F after G homotopic to the identity on B. So this, remember, is what it meant for F to be a split surjection. F is a split surjection, but it's the type of sections of F, because this homotopy means that G is a section of F, and when we take the sigma type of a G and this witness that G is a section of F, we get the type of sections. And dually, we have the type of retractions. We just swap the roles. So I'm going to use a different letter for clarity. So let's say sigma type of an H, again from B to A, and then H composed with F, homotopic to the identity on A. So now F is a section of H, or in other words, H is a retraction of F. But since we fix F and we take the sigma type of the H, this is the type of retractions of F. Okay. So what we've been waiting for, what it means to be an equivalence is simply that you have both. You have a section and you have a retraction. Okay. And another way of saying is we say that F is bi-invertible. Because if you think about the algebra of function composition, the section says that F has a right inverse, and having a retraction says that F has a left inverse, but we don't say that they're related. We just say we have both a left and a right inverse. So as an example, the identity map on any type can be equipped with the structure of an equivalence, because we can take for both the section and the retraction the identity as well, and then the reflexivity homotopy, because the identity composed with the identity is itself. So we have the reflexivity of the identity, and that gives all the witnesses we need for everything. You can also easily check that negation on the Booleans is an equivalence, because we can use itself as both the section and the retraction, because we verify that negation after negation is homotopic to the identity on the Booleans. As another example, you can take the function that adds an integer to an integer, a fixed instance, say fix k, and look at the map from the integers to itself that adds k. Then as the inverse, you can just, for both the section and the retraction, you can take the one that adds minus k, function that adds minus k, and then because adding k and then subtracting k amounts to doing nothing, you can make homotopies to the identity. Okay. So now you're probably thinking, well, this is a bit complicated. Why don't I just say to be an equivalence that I have to have an inverse, so a map in the other direction, a single G, such as F after G is homotopic to the identity, and G after F is homotopic to the identity? And that's a very good question. So let's make a definition of that type, and then we'll look a bit at it and compare it with our definition of equivalence. So the type of inverses of F, which in the book is called has inverse, is sigma type of a function going in the other direction, and then the two homotopies. So f after g, homotopic to the identity on B, and g after f, homotopic to the identity on A. So this is the type of two-sided inverses for f. And as a little lemma, I basically spelled it out already, but it's a good thing to just remark. You have a function that takes such a two-sided inverse and returns evidence that f is an equivalence. Because you can just use the same g as both the section and the retraction. Okay. Now let's discuss a little bit about that discussion. So it turns out, at least after we assume function extensionality, which I haven't explained what is yet, but we will get there shortly, it turns out that is equiv f is much better behaved in the sense that once we assume a little bit of extra structure, it'll always be a proposition in the sense that any two witnesses can be identified. So this is much better behaved than the type of two-sided inverses. Has inverse. That's inverse f. So let me just remind you what this is. This is the sigma type of a g, e to a, and then these, let's see, I put f after g first, and g after f. And we can't really explain why yet, but I can give you a sort of an indication. For sets, it doesn't really matter. But let's look at it in the special case where f is already the identity function. So we look at has inverse the identity on A, then this says I'm giving a G such that G is homotopic to the identity on B, and G is homotopic to the identity, oh, B is A. The identity on A. Now, when we have function extensionality, that'll say that the type of homotopies will be equivalent to identifications of f with g. So if we have that, or if we just believe that in a nice setup, that'll be the case. And then remember that whenever we have an identity type and we have one endpoint that's free, we can identify that with just the case where we are at the reflexivity. You should perhaps see, and I realize this is a bit vague, but this is just to give you an idea of why this definition is poorly behaved in higher dimensions. This will turn out to be related to the type of homotopies from the identity on A to itself. And if A has some higher homotopical structure, that's not going to be that's not going to be a contractible type. There'll be multiple witnesses that the identity has an inverse, whereas it'll turn out there'll be only one up to homotopy witness that it's an equivalence. Okay, maybe I'm sorry if this is a bit vague for now, but maybe it's better to be not to too frustrated about why we have to work with these bi-invertible maps rather than the maps that have a two-sided inverse. Okay, on the other hand, it's not too hard to show that we can always improve an equivalence to have a witness of, to have a proper two-sided inverse. So this is now back to real formal stuff. So if you fix a function from A to B, then you have a map from the equivalences or the witnesses that F is an equivalence to the type of two-sided inverses. Okay, so how do we define this map? By sigma induction. So we have this this product, which itself each pair in the product is an element of a sigma type. So we have 4 components. So when we're defining this map, we may assume we have split all this into variables. So we have G and H. G is the section and H is the retraction. So we have 2 maps from B to A. And let's say capital G is the homotopy from F after G to the identity on B. And capital H is the homotopy from H after F to the identity on A. And then all I need to know really is that, well, let's check. But it certainly seems like it would be an obvious first step to show that the 2 maps G and H are themselves homotopic. And that's indeed the case. So we can define a homotopy K from G to H. And let's say, how do we define this? We use the concatenation. So we have G. G is judgmentally equal to the composite of the identity on A with G. Now I can use the inverse homotopy of H whiskered with G to go to H after F after G. And remember that the 2 ways of parenthesizing the triple composite are judgmentally equal, so it doesn't matter where I put the parentheses. So I don't put any. But we can think of this here as for we first compose H with F, but now I'm going to think of it in the other way. F after G is homotopic to the identity on B. So I can take the whisker of G with little h and get a homotopy to H after the identity on B, but that's judgmentally equal to H. So if I concatenate these 2 homotopies, I get a homotopy from G to H, and I call that K. So now we get what we want. So we already have that G is a section. Let's say that we also want the homotopy that witnesses that G is a retraction of F. So I want an H prime, which shows that G after F is homotopic to the identity on A. But you can also get this by composition, because we can say G after F is homotopic to H after F by whiskering K with F. And then I can use H in the forward direction to get a homotopy to the identity on A, which is what we want. So you can always improve this 4 tuple of data, the section and the retraction with the 2 witnessing homotopies. You can always improve that to just a witness that you have a 2-sided inverse. So we have maps going back and forth, but one is better behaved as a homotopy type, as a type, than the other. Although maybe you don't appreciate that at the moment. Okay, but it's good to know that you can always go back and forth. And please let me know if there are any questions. But maybe it's all very clear to you. I hope it is. Okay, what do we want to do now? Now we want to have some more examples of equivalences. So let's make a definition. The type of equivalences. That you can probably guess. If A and B are types, we define the type of equivalences from A to B as the sigma type of a map from A to B and the proof that it's an equivalence. Okay. Right. And then you have more examples. Of equivalences, where now I'll use this this tilde equals symbols. More examples of equivalences. So you have things like if you have any type and you take the disjoint union with the empty type, you can make an equivalence from that to A. And likewise, A is equivalent to put the empty type on the other side. Have an equivalence. A plus B is equivalent to B plus A. We have this kind of associativity of plus on types. You can define all of these very easily, and I encourage you to do so for anyone you're curious about. So that's some with plus. You could also do some with times. So the unit type, take the product with A. Well, so it's a pair of an element of unit type and a pair of an element of A, so that just amounts to an element of A. You can do that on the other side as well. Also provide an equivalence from A times B to B times A, rearranging the elements in a pair. Another one you could do is take the product with the empty type, and that's going to be equivalent to empty type. So these are all like type level versions of algebra equations. So there's a whole game you can play and take some law of high school algebra and try to see if it can be instantiated as an equivalence of types. But we have to wait to do exponentials. We can do sums and products right now, and we can do exponentials once we have function extensionality. Let me just mention one thing. Some of these generalize to sigma types. So sigma types are like dependent products, where the second component depends on the first. So for instance, yeah, so actually, so before, so I'm meant to do one of these I wanted to generalize. So we did some that had just to do with sums and some that had just to do with products, but of course, there are also distributive laws. So a distributive law is something like take a coproduct or disjoint union of A and B and take the product with another type C. So that's a pair where on the left you either have an A or a B, and on the right you have a C. So really, you either have an A and a C, or you have a B and a C. That works out. And likewise on the other side. So A times B plus C is equivalent to A times B plus A times C. And it's these distributive laws I want to have some versions of for sigma types. So the version of the first one is that if C depends on A plus B, so C is a type family over A plus B, so I can form the sigma type, then that's equivalent to sum either of the first element, so an X and a C of in left X, or a Y and B, and then a C in in right y. You could also do a sigma type version of the other distributive laws. It looks a little bit different. This time you have two different type families, B and C over A, and you can form the sum in the context of a variable, and then you can take the sigma type. So you could say sigma x in A, B of x plus C of x, and then you can distribute that out. So this becomes sigma over x in A, B of x plus sigma x in A, C of x. Okay. So not only do we have these high school algebra equivalences, there are also some that you can generalize to dependent types, type families. Okay. So as you might imagine, there are also laws and operations on equivalences. So for instance, there's a reflexivity equivalence because we already discussed that the identity function is an equivalence. So if you take the identity function and pair it with that witness we constructed that it's an equivalence, then you get an equivalence from any type A to itself. And the next one you have to think a little bit about. So let's do that. There's a map from equivalences from A to B to equivalences from B to A. So let me just maybe say here, first go to a two-sided inverse. So you start with F, a map from A to B, and a proof that it's an equivalence. Then you improve that to a two-sided inverse of F from A to B. But then you notice that a two-sided inverse, that's a symmetric condition. You might as well just say that F is a two-sided inverse of G, and then you go back to the section plus retraction definition of this equivalence, then to section retraction. And then you have the one G that has F as its section and F as its retraction. So that's how you can get the operation that takes an equivalence and provides an inverse equivalence. And you can concatenate equivalences. So if A is equivalent to B, B is equivalent to C, then A is equivalent to C. I won't spell that out here. Okay, etc. And you could provide, actually, yeah, I wanted to say you could prove some higher laws as well, but now I'm thinking probably you need function extensionality. So it's high time we discuss function extensionality and univalence. And this is just a preview, but it's might come up in the active track already. And always, it's always, you probably heard that the univalence axiom is one of the key distinguishing features of homotopy type theory. In fact, it implies function extensionality, but we won't see that today, certainly. But we can define what both of them mean. So because homotopy and equivalence are reflexive relations, we get these functions. So from an identification to a homotopy, this is a function that takes two dependent functions in a pi type. Let's say P is still the pi type, say x and A, B of x. Let me just spell it out. Pi x and A, B of x. So for every f and g, you have a map from the type of equation of qualities or identifications from f to g to the type of homotopies. by path induction. You apply path induction, it suffices to give a homotopy from F to itself, and we have the reflexivity homotopy. And likewise for equivalences, we have a map from identifications to equivalences, saying for every A and B in a universe, if you have an identification of A with B in U, so this is in the pi type, and here's this is in the universe, then you get an equivalence from A to B. Because again, you apply path induction, and because we have the reflexivity equivalence, we get this function. So function extensionality will postulate is some proof that this first function is pointwise in equivalence. So formally, this says for every F and G and P. Okay, I'm going to write P again. P is this pi type. Pi x and A x. So for every F and G and P is equiv this function it to homotopy FG. So it to homotopy applied to F and G is this function from identifications of F with G to homotopies from F to G. And function extensionality says that this is itself an equivalence. So in particular, the type of identifications becomes equivalent to the type of homotopies, but it's a little bit better than that because we know the particular function that's an equivalence, and that's always useful. And likewise, the univalence axiom is an element of the type for every A and B in a universe. So it depends on the universe. So univalence axiom for U, which say for every A and B in U is equiv. Oops, I didn't need that parenthesis. Let's reuse it. It to equiv A and B. Okay, and that's it. That's what it says. And to explore the full consequences of that, that'll take us a while, but at least now you know what it means. Now, the other big thing I want to say in the remaining time is I want to discuss identifications. Identifications in sigma types. But maybe I just want to ask the TAs if everything's going well or if there are any questions. Okay, everyone's happy.
There's a good question about why is it called the univalence axiom, or the question is why is it called UA when it's a theorem?
Well, it's not a theorem in the system we have been setting up. We've been talking about just Martin-Löf type theory, and there it's not a theorem. There are models of Martin-Löf type theory where it doesn't hold. For instance, the set model where every type is a set, and you interpret sigma types and pi types and families of types as families of sets, and then the usual disjoint unions of sets and dependent functions between sets and so on. And there it's just not true. So it's certainly not a theorem, because if it were a theorem, it would be true in all the models, and it's not true in that model. So it's a good question. But however, there are new type theories under development, cubical type theory, or maybe multiple variations of a cubical type theory, or higher observational type theory, where it is a theorem, or it's built in some way. So it's a good question. And I think in the active track, we'll soon get to a setting where it is a theorem, but it's not a theorem for us here in the hot track.
We have an excellent question in the Q&A. Is FunX also an axiom, or does it follow from univalence?
Yeah, it does follow from univalence. It takes a bit of work. That's due to Blavatsky. I mean, the univalence itself is also due to Vladimir Blavatsky, and he proved that you can actually derive function extensionality from univalence. It's not so easy. I think once we have a few more tools, maybe we'll see the proof. I'm not exactly sure, but it's not trivial, but it is a theorem that you can prove function extensionality from univalence. However, from a sort of, if you just want to set up the theory, you might as well assume both, because we want to have a system where function extensionality is true almost no matter what, even if you're working in the set theoretical model. So you might as well start by postulating that. And then it's sort of a cute fact that you didn't really have to if you're also going to postulate univalence. Okay, anything else? All right, then we'll move on to discussing identifications and sigma types. So this we can do without postulating in either function extensionality or univalence. So we fix a type and a type family. So we fix A as a type and B is a type family. So for every X in A, B of X is a type. And remember I said we could, if we want to get some geometric intuition, we could think of A as some base collection of points, or maybe a space of some kind. And then so think of it as an x-axis, because we can have a variable that ranges over A. And then if we want to talk about B, it's sort of like having different y-axes for every x. So over this x, there's going to be this y-axis, which we call B of x. And this is where there could be a point in B of x. Okay, so what we want is we want a relation. And in fact, we've seen that to use path induction, it's very nice to have a reflexive relation. So we want a reflexive relation that depends on two elements of the sigma type. So I'm gonna, for this section, define S to be the sigma type. So S is sigma type A, X and A, B of X. And remember, we can think of this picture as the first projection from S to A. So we want a relation that has two, that relates two different things to two different points in the sigma type, a Z and a C prime, or Z and Z prime. So we want a type R of Z prime. Okay, actually, we're going to call this type equalities in the sigma type. So this should be a more useful description of when two elements of the sigma type are related. So let's say by sigma induction, or it's because we know what the types are in, or what the terms are of a sigma type. So we assume, let's say, assume Z is a pair of an X and a Y. So we have a Y here, let's say. And let's say we have Z prime is the pair X prime and Y prime. So this lives with some X prime here. And we have a Y prime in B of X prime. Okay, so I want this this type depending on Z and Z prime, or all these four elements X, Y, X prime, and X and Y prime, to express the ways I can identify the pair XY with the pair X prime, Y prime. Well, by taking the action on paths of the first projection, we should, in any case, have an identification of X and X prime. So we should have some P of type X equal to X prime in A. Now, what should we do about the second components? The problem is that Y and Y prime live in different types. So what comes to the rescue is that we have the transport operation. So recall that we have transport, let's call it TR, transport in the type family B. This is a map from B from, let's see, well, for every x and x prime, if x is equal to x prime, then I get a map from b of x to b of x prime. Often I'm not going to write the, let's say, use a little bit of active notation. I'm going to keep the x and x prime explicit, implicit. So we're just going to write that there's some p here, and then you can take a y, and then you get an element in b of x prime. So in particular for this y, we have the transport. So if we have a identification, let's see, it goes from x to x prime. So it's like an identity in this direction. And then we can apply this transport function. So we get this element here, transport b, p, y. So now we can compare this term with this one, and that should be the second component of identifying the pair xy with the pair x prime, y prime. Now, the book doesn't do this, but many people who work in homotopy types, they like to think about the corresponding identity type as its own thing. So I'm going to make this definition also, so if you see it somewhere else, you understand what it is. So we define a new type of ways of identifying y with y prime in the type family B relative to a fixed p. Okay, so this is going to be a type, and we define it to be just an identification from the transport along p of y to y prime. So this lives entirely in b of x prime. Okay, so people call this the type of paths, or let me see, I don't know, call it a path. Sometimes people call identifications path. I'm trying not to. I'm calling them identifications. So let me call them identifications. Paths have the benefit that it's easier to write and shorter to say, but identifications of y with y prime over, so identifications lying over the identification p. And then often we'll make in the picture, we'll say actually there's a path not only that lives over here, but there's somehow a path in this, like that lives over the p, and this might be a q. But really we just think of it as, I mean, we could, for us, we're always going to use this definition of it. So whenever people draw something like that, you can just replace it by saying, okay, there's an identification over here from the transport of y with y prime. So whether or not you find this is helpful or not, it's up to you. But now you know what it is. But we're going to use it to define our relation equality and sigma types. So let me put that here, and then I'll copy it over to the next slide. So equality of sigmas, or in sigmas, set with set prime, we now define to be a sigma type. So it's a sigma type of a p. So in general, let's phrase it just before we do a sigma induction on the set and set prime. So it's an identification of the first component. So PR1 of z with PR2 of z. And it's an identification of the second components, PR2. Oh, did I say 2 here? It should be a 1. Too small, you can't even read it anyway. PR1 with set prime. So the first component of set and the first component of set prime, those should be identified, and relative to that, or lying over that, in the type family B, you should be able to identify the second component like that. But it really just means that when I transport the second component of set along P to B of the first component of set prime, I can identify that with the second component of set prime. Okay, let me copy that over. Okay. Here we go. This is our definition, and let me just, this parenthesis is judgmentally equal to transport in B along P of the second projection identifies with the second projection of Z prime. Okay, that's the definition. What do we want to do? We want to show this is reflexive. That was important to be able to compare it to the identity type. So we define a term witnessing that this is reflexive. So the reflexivity of the equality of sigma. So this should be a term of type for every set in the sigma type. We should give an element of e sigma of Z with itself. And we define it to be lambda Z. And then we can do, so if we have, if Z prime is equal to, is judgmentally equal to Z, we can take reflexivity to be the first component, reflexivity of the first component. And then because transport along a reflexivity is judgmentally the identity function, the second component, this type of this, reduces to PR2 of Z equal to PR2 of Z. And there we can use reflexivity again. Okay. So this witnesses that we have a reflexive relation. And now we can define the maps back and forth. So by reflexivity, we get a function called pair eq. I guess that means that we take an equation or an identification and we make a pair of equations or a pair sigma or eq sigma out of it. So this has type for every Z and Z prime in S. If Z is equal to Z prime, then we get an eq Z sigma Z Z prime. And this is by path induction. And in the other direction, we have getting an equation in the sigma type out of a pair of equations for every Z and Z prime. This maps from eq sigma Z Z prime to Z equals Z prime. Okay, so let's do this in a few steps. So first we use repeated sigma induction. To get to a context where we have split Z and Z prime into components. So this means I have an X and an X prime in A, and I have the corresponding Y's. So Y lives in B of X, while Y prime is going to live in B of X prime. So that corresponds to the Z and Z prime. Now, eq sigma is also a sigma type, so we can split that up into its component pairs. So the first component is going to be a P of type X equals X prime in A. And then there's a Q. Let me split it up in terms of the transport. Transport B P Y equals Y prime. Okay, so all that we have. Now notice we now have some choice. We have two paths, and in a sense, the endpoints, or at least the right endpoints, are free. So we can do path induction on. Should I do them one at a time or two at a time? Let's do one at a time. So let's do path induction on Q. So now we say, okay, I have a Q and I have a Y prime and a Q that something is equal to Y prime. So I might as well, and I have to show something, right? So what we have to show is we have to show that the pair XY is equal to X prime, Y prime. But now we get to a new context. We simplify this to be, because we only show this in the case where Q is the reflexivity at the transport P to Y. So now we still have the X and the X prime. And we still have the y in b of x. No longer have the y prime because y prime is going to be judgmentally equal to this transport. We still have the p. Still have the p in type x equal to x prime. And we have the goal to show xy is equal to x prime and then transport in b py. Okay, and then we can do a path induction again. Path induction on p, because again we're doing something for every x prime and a p that identifies x with x prime. So it suffices to do whatever we have to do in the case where p is the reflexivity path and x prime is judgmentally x. So now we are reduced to a situation where we just have the x in a and the y in b of x. The p has gone, that's the reflexivity, and the goal is to show that xy identifies with what? Well, x prime has become x, and p had become the reflexivity identification of x with itself, and transport along a reflexivity does nothing. So this becomes y. And here we have reflexivity. So we're done. You notice that you could also have done it in the other order. It doesn't really matter. You could still have done it. Okay. So now we have maps back and forth. Let's look at some claims. So the first claim, I want to show this is actually a situation where we have two-sided inverses, because then we show that, say, pair eq is an equivalence. So to show one of them, we have to show for every, well, actually, we want to show these two-sided inverses for every set and set prime. So for every set and set prime in S, and for every W in the eq sigma relation, set prime, I want to identify repair of split up the pair W with W. And okay, so now by sigma induction, repeat it. We have the situation on the previous slide where we have the x, the y, the x prime, the y prime, and then we have the p and the q. But to do something for all of those, we can do then path induction again twice, and then path induction 2x. We have to show something for every x and y and so W is now refl and refl, and eq pair of pair refl is refl, and pair eq of refl is refl. So we have to show that refl is equal to refl. But those are the same thing on both sides, so we can use reflexivity. And we're done with that case. In the second case, we go the other direction. So for every set prime, and for every identification R, say set equals to set prime in S, I can compose these functions in the other direction. I can remake an equation out of a pair of equations, and I can make a pair of equations out of one equation. And I want to identify that here. And then now we have something where we can apply path induction. We have this claim for every set prime and a path and an identification of set with set prime. So we just do path induction. And the goal is to show, well, what happens in that case. So pair eq of refl is the pair of refl reflexivities, and eq pair of a pair of reflexivities is reflexivity. So we just have to show that refl of z equals refl set. So R is refl set, and this becomes equal to refl set. We have to identify reflexivity with reflexivity, and again, we can use reflexivity. And we're done. Okay, so as a corollary, now we have the two-sided inverse situation, but we can phrase that, if we like, as an equivalence. So for all z primes in the sigma type, we can now have an equivalence. Z equals z prime in S is equivalent to eq sigma z prime. Okay. Often that's the kind of thing we want to do in homotopy type theory. We have some type here, it's S, a sigma type, and we want to get a concrete understanding of the identity type. And this was quite a lot of work here. And in a later lecture, Emily will give you a bunch of tricks for how to do that much faster and better. But this one we could still do by hand just by brute forcing it. So that's what I had to tell you today. Thanks so much for listening.
Great. Thanks, Ulrik, for that preview. Let's see, do we have any questions while we're all still here together? I guess in the meanwhile, I will applaud for the group. PAs, do you want to bring forward any questions that were answered in the chat and enter them into the recording?
Maybe if you could just say again why you defined this equality for sigma separately. Yeah, I think there was just a question clarifying that in the chat, so it might be good to say again.
So I guess the question is, why don't we just use we already have a type, the identity type on the sigma type? Is that the question? Well, it's a bit, without doing this work, you don't have I mean, maybe I want to ask the TAs if they have a better answer to this. I think so. In this particular case, I don't have a particular application of this in mind, actually, that just comes to mind. And maybe it's because it's 100 degrees. But it certainly for many types, it's just not very direct. We have this type family, the identity type family, that's defined for every type. And all we know about it is that it's somehow inductively generated by reflexivity. So it's very useful to have any kind of better grip on it. So for sigma types, we can prove that we have this equivalence to this sigma type of identification. So an identification of sigma type is a sigma type of identifications, and that's somehow I think that's very very pretty, and it's also it is definitely useful. I'm blanking on a particular application of selling point at the moment, but for many times we really would like to have these concrete descriptions of identifications in the types.
Two people have raised their hands, so someone who's a co-host can add them.
I think I have one example in mind. So, but it maybe it's something that involves univalence. So we have the type of groups or something like type of monoids. So let me write something down. It's a little bit more of a preview of univalence, but since we've defined univalence, we can talk about it. So let's say we define the type of monoids. So we fix a universe U, and we have a type of monoids in U, and it's going to be an iterated sigma type. So you're going to have an element of U, and then there's going to be another element that that we have not defined yet, so don't worry about it, but it's going to be that X is actually a set. And then there's going to be some other element. So there's going to be a neutral element, E and X. And then there's going to be multiplication. So it's from X to X to X. And then a bunch of laws. So I'm going to not spell it out today. So we want to show something about, you can imagine that we want to have a good handle on when two monoids can be identified. And having this description of, so if you just stare at it, is this big iterated sigma type. But with this theorem, we know we can do it step by step. We say, well, first, I need an identification of the underlying sets. And that's going to be a bijection, which is the same as an equivalence in that case. And then, well, relative to that, we have to transport, but then transporting just an element just it means applying the equivalence. So they have to have some function that turns out to be a bijection from X to Y, and such that the neutral element of X is, when you map it with a function, it can be identified with a neutral element in Y. And then you have to think about how do you transport in an iterated pi type. That's something for another story, but maybe you can get the idea of why to understand the type of identifications in such a, on the face of it, quite complicated type. It's very useful to have this theorem we just proved.
Great, absolutely. I might stop the recording here, and then we'll stick around and take other questions if there are any. But for posterity, we'll have another lecture starting something brand new by Dan Licata on Friday.